This is problem 23.40 in the textbook, and it is pretty closely related to example 23.2, which is fully solved in the textbook as well. So the idea here is that we want to show that the maximum magnitude Emax of the electric field along the axis of a uniformly charged ring occurs at a certain position. The first thing we do has to be to figure out, well, like, what is the expression for the electric field? Right? Like, what is it? What's its magnitude? Where is it pointing? And then we're going to be able to figure out when is it at its maximum. Now, if we look here, this is our situation where we have this ring and we want to know the electric field at this point here. Now, if we just look at it close enough, we can see that, well, we have little chunks of charge all along the ring. And let's say this is chunk dq1. And the electric fields here, remember, is going to be pointing in the direction of motion of a positive charge. So if I had a positive charge here, it is going to be moved in this direction here. It's going to feel repulsion. Same thing for this dq. It's going to be repulsed in this way. And because of the uniformity, well, the circular nature of this situation, all of the perpendicular parts of the electric field are going to cancel out, and we are going to be left with a net electric field pointing in the x direction. So if we were to write that out, we would say this. We'd say that dE is equal to KE dQ over R squared. Now this is just saying that a small portion of the electric field at this point is equal to, when we take a little chunk of charge and we see what is its impact on the electric field. Now, if we want to find only dEx, because we know that's the only part that's going to survive, we just need to take the x component of it, which is going to be taking this times the cosine of theta, because again, here, this is the sine theta component, and this along the x-axis is the cos theta component. So if we do this, this will give us E in the x direction. Now there's a couple things we want to do. Usually you're given A, which is the radius of our ring, and we are given X, which is where is P along the x-axis, right? So we're given these things. That means that we can represent R and theta in terms of A and X. By that, of course, R is going to be equal to the square root of A squared plus X squared. And also, we know that cosine of theta is equal to X divided by R, which is equal to X divided by square root of A squared plus X squared. Now, if we plug all of that into this equation here, we see dEx is equal to KE dQ. Cosine of theta is X divided by square root of A squared plus X squared times R squared, which is A squared plus X squared. Another way to write this is KE dQx over A squared plus X squared to the power of 3/2. All right, so this is our expression. And the thing that I find people get confused on the most in this problem, it's because we're just expected to solve the integral from here. You're told, okay, take the integral here and figure out what Ex is. And that's really confusing because we talk a lot about lambda and we talk about sigma and we talk about rho, where this is the linear charge density, right? This is the area charge density and this is the volume charge density. And it's like, well, why can't I just do what I always do and plug in dq is equal to lambda dl? Why doesn't that work? And the thing is, it does work, and it's a perfectly fine way of doing it, and that's the quote-unquote normal way to do it. But what we find is that this method is a lot easier to solve, and we can use it for one specific reason, and that's because if we look at this configuration and we look at our dq's, and we think about how far away they are from the point, we see that every single one of them is spaced r away. They're all spaced the same distance away from this point. And that's very, very different to all of our other scenarios. Like if you think about charge density of a rod, right? And you're like, hey, what's the electric field at this point P here? Well, if you look at different chunks along the rod, if I look at these 3 different chunks that each have a little bit of charge, dq1, dq2, dq3, well, they're spaced differently, right? Like there's how far away they are from P changes depending on what chunk you're talking about. So then we do need to talk about, well, we talk about lambda dl, and then we say, okay, well, this is going to be dx, where we consider which one are we talking about, because each one of them contributes in a different way to the total electric field here. Versus in this case, they all contribute equally, so we can just take the integral of dq. In the next video, I will be solving it with the lambda dl method. So if you are curious as to how to solve it that way, I do recommend looking at that. So, like I mentioned, we are going to be able to solve this by taking the integral of both sides. And that leaves us with e of x is equal to the integral of ke dqx over a squared plus x squared 3/2. Take all of the constants out, and then we have kex over a squared plus x squared 3/2 integral of dq. Now we're integrating over this entire loop, right? So we're going from one angle and we're looping around, and really here we're just adding up all the different dq's, and that's going to give us capital Q, which is the total charge. All right, so our answer is pretty simple, but if this is really confusing to you, I really do recommend looking at the case where we solve it using lambda dl, because that might be more intuitive to you. So our answer, Ex, is equal to Kex Q over a squared plus x squared to the power of 3/2. Okay? So this is a solution, but I mean, that's not really what the problem was asking us. It was asking us to show that the maximum energy, Emax, of the electrical field along the axis of uniform charge, so along x, is that x is equal to a over square root of 2. Now, if you remember from your calculus classes, we know that the derivative is equal to 0 when we have a maximum or minimum. So we're going to take dx over dx, because we care about where is it 0, like where is it maximum along x, and we're going to set this to 0. To do this, hopefully you remember your chain rule, and we know that, I'll just re-explain it quickly. So the derivative of, let's say, x, of two things that both have x in them is going to be equal to, you keep the one constant, take the derivative of the second one, plus the first one constant, derivative of the other one. All right, so here, I'm just going to rewrite this as KEQ, and then we have x and a squared plus x squared to the power of negative 3/2. Now we take the derivative of this with respect to x, and the first thing we do is say, okay, these are two different things that have x inside them. So we're going to do KEQ, and we're going to keep the pink one constant, so a squared plus x squared to the power of negative 3/2. We take the derivative of x, which is just 1, plus this time we're going to keep the green one constant, so it's going to be KEQX, and then we take the derivative of the other one, so that's going to be negative 3/2 a squared plus x squared to the power of negative 5/2, times, we then have to take the inner one too, 2x. Okay, and this is equal to 0. Now the next thing I do is rearrange some things a little bit, and we get 1 over, well, first I should tell you one more thing. Here, what we're going to be able to do is take these KEQs out. What I mean by that is say, okay, well, KEQ, they're common in both equations, and then we're going to have a squared plus x squared to the power of negative 3/2 plus x times, here we have an x here and an x here, so that's going to be x squared. We have the 2's cancel it with 2's, and we do have a negative sign here too, so we have negative x squared times 3 a squared plus x squared to the power of negative 5/2, right? And we know that this is equal to 0. Now, either this is equal to 0 or this is equal to 0, and because we're minimizing for x, and these are just constants anyways, they can't be 0, so this is equal to 0. If I rewrite that, I have 1 over a squared plus x squared to the power of 3/2 minus 3x squared over a squared plus x squared to the power of negative 5/2 is equal to 0. Now I just rearrange things again, and I get 1 over, well, I don't really want to rewrite it, so I'm just going to move one of them to the other side. I'm going to say, okay, this is going to be equal to this one. Now again, I keep rearranging things. I have a squared plus x squared to the power of 5/2 divided by a squared plus x squared to the power of 3/2 is equal to 3x squared. Now here, I see that, okay, I get a squared plus x squared is equal to 3x squared. A squared is equal to 2x squared. Therefore, x is equal to a over square root of 2 is going to give me that position that I'm looking for. Now, if we go back to the question, it says, okay, show that its maximum value is at that position that we showed and has a value of this. Now we're just substituting things in. So we know what our expression for E is, right? So way up here, I'm going to drag this down and we're going to plug in x to the equation. So then E max is equal to, then we have KE A over square root of 2 times Q over, and then we have a squared plus a squared over 2 to the power of 3/2. From here, there's literally no physics involved. We're just moving things around and doing math. There hasn't actually been physics in a little while, but we are going to keep going. So KEA Q divided by square root of 2. Then we have 3/2 a squared 3/2. And then here we can cancel out some of these a's because here we have a squared to the power of 3/2. That becomes a to the 3. So this becomes KEQ over square root of 2, a to the 2, 3/2 to the 3/2. And then we just have to keep going. And we see that this is equal to KEQ over a squared 2.5, 3 and 3/2, 2 negative 3/2 is equal to, and I'm just simplifying to get it into the shape that I want it to be in, and that's about it. 2KEQ over a squared root 3 over 3, 3 to the power of 3 is equal to 2KEQ over 3 root 3 a squared, and that is pretty much what we want because we know that k is equal to 1 over 4 pi epsilon naught, therefore E is equal to Q over 6 root 3 a squared epsilon naught times pi, which is the form that we want it to be in.